We are back. Our next guest is Professor Georg Northoff. If you ask who is Georg Northoff, the question is quite impressive. He's a philosopher, a neuroscientist, and a psychiatrist, holding those 3 degrees in all 3 disciplines. That's why his perspective is extremely valuable. We don't see very often a professor with 3 distinct specialties that are so much interrelated. He leads up the Mind, Brain, and Neuroethics research unit at the Royal Institute of Mental Health Research, which is a research institute affiliated with the University of Ottawa. But what Professor Northoff is researching? He's researching the relationship between the brain, the mind, and all his multiple facets, neural, biochemical mechanisms, mental functions like consciousness and self. And the most important is that those research are done in mental illness patients and in healthy persons. Let's welcome Professor Northoff. And Professor Northoff, you have the floor. Please unmute.
Yeah, thank you very much for the nice introduction, and let me share my talk. Can you see my slides?
Now, yes.
Yeah. Okay,
yes.
Perfect. Let me just get the slide up. Okay, yeah. So I'm talking about, of course, of what you all have is consciousness, and despite a lot of research in this area and also linked to artificial intelligence, the exact connection between neuronal and mental activity is not really clear yet. There's a lot of theories, as you probably know, but the exact link how neuronal activity transforms into mental activity is not clear. And that's exactly the idea of my talk. And you see here this Frankenstein is a very famous movie. Actually, it was done in a castle in Romania, and I can highly recommend downloading that movie because it's on a hill somewhere in Romania. I don't know where, but the movie is quite good, and the landscape, what you see, is fascinating. So my talk will be a little bit about the theoretical background. I don't want to go too much into philosophy, but a little bit because this is very important to see here. And then I will show you some data of our idea theory of consciousness, about the level state of consciousness, and then the form or structure. And then I conclude with some implications for artificial intelligence and other species. And you will see it almost as a natural outflow of the data and the idea. For the theoretical background, one key feature, of course, you all know in the Western tradition, there's been Descartes, mind, body, and of course, nowadays we say, oh, no, we are so much more advanced than Descartes. No, the mind is the brain. However, you'll be surprised, Descartes is still very much present in our philosophy and neuroscience, because what Descartes wanted to indicate when he assumed the mind is that the mental features are special. We cannot access them in the third-person perspective. We cannot observe them. So they can only be accessed from the first-person perspective and experience. And that means, and he inferred from that they must be different from the body, hence assuming a mind. So, of course, nowadays we no longer assume a mind, but a brain, but we still presuppose that the mental features are special. So we assume special neuronal mechanisms in the brain, like information integration. Let me go to the next slide. Nowadays it's a little bit more sophisticated. We have 2 different levels of the mental: reflective phenomenal, access phenomenal consciousness, and block. And in neuroscience, this is well reflected in the global neuronal workspace theory. Of course, the advocates will kill me that I put them under the access consciousness. Same for the hot higher order theory, integrated information theory. But despite all the differences between these theories, they still share that the neuronal mechanism for the mental features / for consciousness are special and different, principally different from the rest of the brain, from the non-conscious mechanism. That's a big problem. The only theory which currently somewhat tries to bridge that gap is here predictive coding for energy by Prof. But otherwise, there's a clear gap here. And you see this in basically the paper we published 2020, basically in all theories of consciousness. So neuroscience of consciousness is embedded in integrating a special neuronal mechanism, information integration, global neuronal workspace, which is basically an add-on, a special mechanism just tailored for consciousness. So the question is whether maybe we really, and that's obviously Descartes, it's a neuronal Cartesianism. So the question is, maybe we can leave all that behind and assume there's something similar. Yeah, there's no principal difference between neuronal mechanism related to consciousness and neuronal mechanism related to non-consciousness. Maybe it's just a matter of degree. So we assume similarity, and that's a little bit of the background of our approach. So then you say, yeah, what is similar? So here I go back to a very nice quote, and that's of course what we assume is the most basic features of the world. If you want to find the secrets of the universe, think in terms of energy, frequency, and vibration. Beautiful quote by Tesla. Again, highly recommended. Look him up on the website. Quite an eccentric guy. Last 20th century, beginning 20th century. And that's exactly what our assumption is. That dynamics, change, energy, literally energy, we can measure energy in the brain, provides the link between the neuronal and mental features, the bridge. And that's why we speak here of a common currency. If I were to start speaking Germany, I'm originally from Germany, you would not understand me, we could not communicate, we would not have a common language or common currency. That's exactly what we're looking for. So, and what is this? And you will see this in the throughout my talk. This is a special topography, a special spatial arrangement. The brain has its own, constructs its own inner time and space. Philosophically, obviously, that basic idea goes back to Immanuel Kant in philosophy. And I transferred that sort of to the brain and temporal dynamic, and you will see that these mechanisms are key for consciousness. So, and that's basically, so we developed what we call a temporal spatial theory of consciousness. And the key here is that really topography and dynamic, time and space, the inner times, the brain's inner time space construction relate neuronal mental features. Important from the empirical side that this theory directly provides links, spontaneous and stimulus-related activity, which are often considered separately in the current neuroscience. And also, as I said, it provides a direct link between neuronal and phenomenal or mental features. So it includes both neuronal and neurophenomenal hypothesis, and I will indicate that a little bit. So just for an overview, unlike the other theories, which only assume one particular mechanism to underlie consciousness, like integration, information, global neuronal workspace, or higher order processing, the TTC, temporal spatial theory of consciousness, has different mechanisms for different aspects of consciousness. And that's very important because this is what about science is. Science is slicing up the things without slicing the whole into parts without losing the whole. Yeah, so you really need to operationalize that, very important. So that's basically a short overview about consciousness, temporal spatial theory of consciousness. And now I want to get a little bit more concrete in terms of the empirical mechanism, because I don't need to tell you any theory is only as good as the data you have. And particular what we want to have particular mechanisms which are associated with consciousness. So the first thing is temporal spatial nestedness. What is temporal nestedness? I don't know, you can probably see here the Russian dolls. You see some Russian dolls, typical example of nestedness. There's a larger doll nested within a nesting a smaller one, and so on and so forth. So, and the same happens in the brain. When you go to the seaside, you have beautiful sea there in Romania. You go to the seaside, you see big waves, you see small waves. Yeah, And you see that the bigger waves are much more powerful than the smaller waves. Yeah, so you're afraid of the bigger wave that they might smash you towards the beach. And that's exactly the same in the case of the brain. You see very big waves, and they're usually very slow, infra-slow frequencies, for instance, which we can measure in fMRI. And then you see much faster frequencies, much faster waves that are much less powerful. Here, alpha, beta, etc., usually measured with EEG. And you can get that all of this, what we call a time series. And what is important, so you can already see here the bigger waves contain and nest the smaller waves. Yeah, so it's exactly like the Russian dolls. The bigger one includes the smaller one includes the next smaller one, and so forth. And that's exactly the way. There's a certain organization, a certain structure, very important. Yeah, so slower waves, more powerful, faster waves, less powerful. So there's a certain gradient. Here you can see this down here. Here's frequency, here's power, and here you can see the typical relation. And this is, you can measure that with what is called scale-free activity or power law exponent. Now the question is, are these kind of phenomena relevant for consciousness? Yeah, is the organization of these different waves, slow and fast, powerful, less powerful, important for the consciousness, for the level of consciousness? And this is exactly what, for instance, we studied in this study. This was the subjects in anesthesia, the same subject in awake state or anesthetic state. They were in fMRI. And you can already see, and we measured basically the slope, you may remember, the slope of this curve, which is called the power law exponent. And what you could see, there's a huge difference here in the awake state, anesthetic state. And what particularly interesting in, you may remember there's sort of this curve, more power in the slower, less power in the faster. Yeah, so you see a certain structure here, a temporal structure, and that is completely abandoned in anesthesia. Nothing of that is done anymore. Yeah, so it's completely flat. So that's basically, imagine a seaside where all the waves have the same size. It's completely boring, and they have the same power. There's no difference anymore. That's the way your brain looks like in the unconscious state. So this has been confirmed also in sleep by others and also in coma patients. So it's really a loss of the temporal structure, and that means it's a loss of your nestedness. Yeah, so all the waves are the same. It's very monotonous, and there's no difference in power. There's no variability. It's basically like ultimately, this is like a flat sea. Yeah, nothing happens, complete silence. That's the way your brain looks like when you're unconscious. You probably don't want to try that out. Yeah. And let me just skip that. Then the other question, okay, this is about temporal nestedness. Yeah. Faster frequencies being nested in slower frequencies. Now, what about the spatial domain? You know, the brain has several regions. I don't need to tell you that, different networks. And how is that related? So here, and there's sort of, in the current series of consciousness, often assume, okay, it's particular region. It's the posterior regions in the brain here in the back, or it's the anterior, like the prefrontal cortex. And they often assume that, and that's, and they say, okay, it's one region. However, you need to consider the whole brain. Each region only recruits its own neuronal activity in the context of others. It's exactly the same way. If I were just here alone, completely alone in front of my Zoom screen, and there would be nobody else, I would probably not give this talk to myself, and I would speak differently. Now, if I know that there's a certain audience, it impacts me how I speak. So same way, the whole brain impacts the single region's activity. That is often neglected in current theories of consciousness, because they think it's just either that region or this region. So here, what we, for instance, did, here we investigated the global brain activity. It's basically through, for the experts among you, global brain synchronization, which you investigate with the global signal in fMRI. I spare you the details, but what you observe, the more global activity, meaning the more red, the higher your level of consciousness. So here you see the sleep stages. You see wakefulness, the brain is very red, high degrees of global activity. And then you get into the first sleep stage called REM1, and you see still a lot of red activity, and then becomes less. And sleep stage 3, you're completely unconscious. There's basically the global brain activity is much lower. Here we see the same days seen in rats. These are humans. These were rats. In humans, you see if you have higher doses of an anesthetic drug, you really lose your global brain activity. Same here when you have brain lesions and you enter into coma state, minimally conscious state, unresponsive wakefulness state, and you see here in the healthy control, it's very red, a lot of global brain activity, here low. Yeah, same here in the human anesthesia. Here you see the results. There's almost a parametric mapping. So your degree of global brain activity, it's very important for your level of consciousness. The more global brain activity you have, the higher your arousal, the higher your level of consciousness. Yeah. So for me, it's early morning, it's 6 a.m. Probably my global brain activity is not as high yet as it should be, or as it is during the day. Yeah. So that's very important, and we can really use this. And we are now about conducting a large clinical study to really use this as a clinical marker. Yeah. So again, and I didn't indicate that, what you really see is that the local activity is embedded into a global activity. So this is typical nestedness. Your regional activity depends upon the global activity. So when somebody asks me, Dr. Northoff, is the consciousness in the prefrontal cortex or in the posterior cortex? I said neither, because both regions' activity depend upon the global brain activity. So it's the relation of those regions relative to the global activity level, which is important. And our data clearly show that. Yeah. So you have sort of a spatial nestedness, and you have temporal nestedness. Remember with the power spectra, which I showed you, the slow and fast frequency. So, and here you say, I think this is done by, this figure was done by my co-author Federico Ciglio, who is a postdoc in actually a postdoc in philosophy, but who also does neuroscience in Italy, in Pavia. And you really see, look, there's different time scales, slow, fast, short, long in the brain in the awake state. And you lose those time scales when you become unconscious. Yeah. So there's no difference anymore. It's like a black, big soup. That's the way I imagine that state. So I spare you this one. Here, this is an interesting thing. So basically what we say, maybe topography, the spatial organization of your regional to the global activity, of local to global activity, is very important for your consciousness. So in particular, so how you proceed process the input from the environment. So here we did a meta-analysis and also study. It was done by one of my grad students, Austin Cooper. So he studied all fMRI studies in meditation, and in particular was interested in proficient meditation. So how, when you do meditation over the years, how that changes your brain's structure. So meaning its topography, its spatial arrangement. And what he observed, this was quite interesting, that here you see a clear difference, for instance, between a default mode network, a set of regions in the middle of the brain, and the control executive network, set of regions more on the outer surface of the brain. And here you see a clear difference. That's the non-proficient, that's the early meditators. You see that those regions are much more tilted towards the default mode network. And that's typically internally oriented cognition, as distinguished from the external one. Yeah, and that's what we usually do. We make a clear difference between our internal self and the external environment. And you see this also in the topographic organization of these regions. Now, when you become a proficient meditator, they're equally connected, they're on equal balance, and they're also no longer negatively correlated, but positively. Yeah, you can see this here. Here they're usually negative, meaning the more internal cognition you have, the less oriented are you towards the external world, which of course makes sense. If you're more oriented towards the external world, you're less oriented towards your internal cognitions. Yeah. So when you're not interested in what I'm talking here, you just follow your internal thoughts, and you will not be able to pay attention to my stuff. Of course, I hope for the opposite. Yeah, and that's basically the negative relationship between these two networks. However, when you're a proficient meditator, then suddenly these two networks and also sensory regions and this DMN are more in a positive relationship. You can see this here. So this is a positive relationship. They're in a positive relationship, meaning they're very much synchronized with each other. So suddenly you don't longer make such a clear difference between your internal self, and the external environment. And that's a very typical aspect of proficient meditators. It's called non-dual awareness, which is very interesting. So this is a usual state. We make a clear difference between self and other, self and environment. You can see this here on various levels. But however, when you're in a non-dual awareness state, your brain doesn't make this anymore. Then you feel unified, you feel in synchrony with the world. And that's exactly what proficient meditators tell you. There's no difference between myself and the world. Yeah. In Western tradition, then Western people often assume it's a non-self, but it's a deeper layer of your subjectivity where you experience the similarities with your outer environment. Yeah. So you see it's a reorganization of your brain, and you see how important the topography of your brain is for how you experience the world, for your consciousness. Yeah. So I find it very fascinating. Now we also do in dream, you have a reorganization of your topography of the brain, and then you get all these strange, bizarre experiences. So I think I told you a little bit here, already made somewhat a transition to the form or structure of consciousness. The temporal spatial theory of consciousness assumes a specific mechanism for that temporal spatial alignment, already indicated. What do I mean by that? When you perceive me, you're somewhat synchronized, for instance, with my movements now. Yeah, your brain unconsciously, you have no control over it. Your brain unconsciously synchronized with my movements, and yeah, it's like synchronizing with the rhythm of the music, and then you basically become conscious of the music, you get a feeling, and you feel the whole groove of the music. So you feel great. So your consciousness is virtually expanded beyond yourself to the music. You become part of the music. And then the question is, how does the brain do this? How does the brain can synchronize with the music? How can the brain align to the music? Yeah. How can you synchronize and align to my speech, which is key if you want to understand. If you cannot synchronize or align to my speech, you will have no idea what I'm talking about. It's just a word salad for you. Yeah, you say, Northoff, shut up. Yeah. So one key dimension of that is that the brain has its own time scales. And also basically you have to understand that like a window. The brain has not, let's say you're sitting in a room and you have 5 different window sizes. Through each of these window sizes, you see something different. Yeah, let's say there's a tree out there. Through the small window, you just see the upper branch. You don't even know whether it's a tree or not. You just see the upper branch, and maybe it's a little bush or whatever. Yeah, or it's a flower, you have no idea. Then you see the very large window, you see the whole trunk and you see the tree as a whole, but you don't see the details of the upper brush. Yeah, of the upper branch. Sorry, not the brushes. Yeah, it's morning for me, early morning. Yeah, so that's is quite amazing, and that's the same way you have to imagine that the brain has longer time scales and shorter time scales, and through each time scales, the brain can process some input, some different inputs. Again, music. You have the single note. Okay, that's a very small time window. Yeah. Then you have a melody. Okay, that's a slightly longer window. Then you have a whole fugue. Yeah, Bach. Let's say Bach. That's a much longer window. So for each, your brain is brilliant. Yeah, it's all these different time windows through which it interacts or interfaces with the environment. And you can measure these guys, these time windows, through what is called the autocorrelation window. I'd spare you the detail. And what is interesting is that the brain itself has all these different time windows in its different regions. Yeah, for instance, your sensory regions here, like the visual cortex or the motor cortex, sensory motor cortex or the auditory cortex, those time scales are very short, very small time windows. Yeah. Why? Because you constantly get input and you need to process that. Yeah. And you want to distinguish the input. You want to say, okay, this is Northoff's right hand, this is his left hand, and you want to somehow distinguish. Now he moves with the right hand, and now he moves with the left. Yeah, I know it's for you the other hand, because it's the reverse. Yeah. So, but your brain can distinguish that. Now imagine if you don't have the shorter time scales of these movements, you would put the movements of these two hands together. And that's exactly happens in certain disorders. Yeah. Then you have the longer time scales in more the higher order regions, associative regions, like here the default mode network. Yeah. And why are these timescales? I basically indicated it all. Why are these timescales so important? Because basically you match. Yeah. If you don't have the timescale in the rhythm of my hand movement now, your brain doesn't have that timescale, then you will not be able to synchronize with my hand movement. Meaning you might not understand the meaning what I'm saying, and you might not be able to see how my hand movement is synchronized with my speech. Yeah, because your brain does not have the time scale for that, meaning your conscious experience of Georg on the screen will change radically. So I probably better stop this now. Yeah, so and that's what is called stochastic matching. Yeah, you try to match your own time scales with the time scales of the environment. And this is basically something like that, very, very important. Now imagine if you lose these time scales, you cannot match anymore. Meaning, and the question is that relevant for consciousness? So this was addressed by, I already mentioned Federico Ciglio, postdoc in Pavia in Italy. He came as a philosopher to me in Ottawa and left as a neuroscientist. So you can see it's dangerous when you come to Ottawa, or depending on how you see it. I so far didn't convert a neuroscientist into a philosopher yet. So anyway, so he investigated these timescales in subjects with various states of consciousness. So here, for instance, sleep. So this is basically the autocorrelation window, the way it is plotted. Here, remember the power law exponent, we had that before, but I spare you the details, but particularly the window. So this is sleep. So this is the way you sleep. You see a relatively shorter autocorrelation window. So you can be quite temporally precise because your window is relatively short. This was done in EEG. Yeah. However, now when you enter the sleep stages, your sleep stages, non-REM sleep, you see is basically your time scales get longer and longer. And what does it do? So suddenly all the temporal differences, like of this movement, you cannot process that anymore because your time scale is long. It doesn't give you the sensitivity for distinguishing these different movements. So it's basically you experience these movements as one movement. Yeah, that's what you perceive when your time scale is longer. But the real movement is like this. Yeah, but your time scales don't segregate. That basically it's just swallow it up. Yeah, and it's particularly long when you're in REM sleep. Then in dream, it's always very interesting. There's a REM sleep here. You see you still see longer time scales than in the awake state, but different than in the completely unconscious state. Now we did the same in anesthesia. Yeah, you have different kinds of anesthetic drugs, sevoflurane and ketamine, and you see again time scales become longer. Yeah. Then he said, yeah, maybe are these time scales really related to input processing? Yeah, you process an input, and particularly you process the timing of the input, the relationship in the timing between these different inputs. And is that specific for input processing, or is it also a general, also let's say for motor output? For that, he came up with the idea of investigating, it's a very sad disease, amyotrophic lateral sclerosis, ALS, where people completely lose their muscles. They cannot move at all anymore, but they're fully conscious. It's also called locked-in syndrome. It's a horrible state. I've seen several of these patients, and it's not a good state. You may know Stephen Hawking, who had this too. So you lose completely your muscles, meaning your output doesn't work anymore, but you're still conscious. So the question is, are these time scales related to consciousness through input processing, as distinguished from output processing? If that is the case, you would assume that the time scale should remain normal in these ALS patients, in the motor output disabilities. And that's exactly was the case. You could see this here. These ALS patients, motor output, the time scales were normal, consciousness was preserved, meaning their input processing is preserved, and that means through the time scales. So as I said, these time scales are literally your windows to the external world, and these are temporal windows. Very, very important. So that's basically, you can see here as a summary. So you see when you have input processing deficits or sensory deficits, your time scales are abnormally long. So you cannot perceive any temporal differences like this in a fine-grained way. Instead, you perceive this like this, because your time scales are too long. Yeah, they swallow up the temporal differences. It's in motor deficits, it's not. So there's basically too much temporal integration. Everything is put into one big soup, and there's no temporal differences anymore. So that amounts to this quite nice figure, which Federico draw, which I always like. You see here, you have a wide repertoire of time scales. Longer one, shorter one. You need the shorter one to distinguish between the different words. But you also need the longer one to put all the words together. Police, stop right now. We can make sense of that because you can link all those words in your longer time scales, but you can also separate them because you have the shorter time scales. And the same on the visual side. Now, if you start losing your shorter time scales, as you do in the first stage of sleep, non-REM, it becomes a little bit more blurry because there's no temporal segregation anymore. Then now you lose even more of your faster and shorter time scales. It becomes completely blurry. And then you lose all the faster. You have only one log. It's completely black, one big world soup. That's the way I imagine when you lose consciousness of your time scales. So come towards the end. What are the implications for artificial intelligence and other species? That is very interesting. So what I said, what do these time scales do? They integrate the different inputs. As I said, they integrate this input, they integrate this input, and then they sort of put them together. But you can still distinguish between these hand movements because you have the shorter time scales. So there's temporal segregation. But then you can also perceive, look, there's a certain rhythm here, what Northoff does. The right hand always moves when the left hand doesn't. So you need a longer time scale to connect that. So you have a short time scale, and you have a longer time scale for the coordination. So it's about temporal integration and temporal segregation. Yeah. And here, so now it becomes really interesting. This is beyond data. So this is computational model. We had a computational model of the brain, and we basically simulated the different regions. Yeah, these are sensory regions, higher order regions, default mode network, and we gave the model certain inputs, short input, yeah, and a long input. And look what happens. So in the sensory regions, they have shorter time scales which correspond to this short input. And you see basically a one-to-one relationship between neuronal activity and the input. Yeah, there's neuronal activity duration as long as the input lasts. Now, look what your cortical midline structures or the default mode regions do. They don't care about the timing of the input. They completely do temporal smoothing. Yeah, so they put them all together. Look at this. Yeah, they put them all together. So this is temporal integration. This is temporal segregation. And the same holds when you give a longer input. You can see V1 sensory regions, visual cortex, one-to-one matches. And here you see a clear difference. Here's the windows. We also measured the windows. You can clearly see the window is much longer for these regions and much shorter for these regions. Yeah, so you really have different windows in your brain, which do different things to the input. Now, why is that relevant for other species and artificial intelligence? Now, this is a schematic thing from a paper 2021. It was done by Meshat Golozorki, a very clever engineer. who joined my group at the time. He's now in industry, wants to make some money rather than research. And look, when your brain has different time scales, from the cat, the mouse, the monkey, and the human, you perceive the world in a different way, because you can only perceive the time scales in the world which your own brain has. If your brain has a very limited number of time scales, you will have a very limited alignment or access to the world. Yeah. So because your primary input processing is about a temporal interface. Yeah. If you have only one window out of your room looking, there's not much variation in what you see, because it's just one big window, you see just one big scene. Yeah. However, if you have a smaller window, you have an intermediate window, and so forth, you will see different kinds of things, basically like zoom in, zoom out. Yeah. If you have different time scales, you have different ways of zooming in, zooming out. Yeah. If you have only one time scales, you cannot zoom in or out. Yeah. So it's very boring. Yeah. So, and apparently the different species have different time scales. The paradigmatic example of Thomas Nagel, what is it like to be a bat? The bat can process ultrasonar waves. We as humans can't. Yeah. So the bat has a time scale for the ultrasonar waves, which we have. We don't have. So their access to the world / their consciousness there, what it is like, is different based on the different time scales, which I think is a key component often neglected in current consciousness. So now, how does that impact artificial intelligence? Is an easy one. Because basically you can try to build an agent, I didn't include that here in this figure, with more time scales or different time scales or more fine-grained time scale. Instead of 20 different windows, you build an agent with 30 different windows. Yeah, and that agent will interact with the environment in a slightly different way than you do. Now you build an agent with 40 different time scales. That agent will also interact with the environment even more different than you with your 20 time scales. Yeah. And this is already implied that you can use maybe such agents then also for psychiatric therapy where time scales are abnormal. Now, last example from an artificial agent, what you can do. Let's say you have a robot. Yeah. And so this is a robot, this is a human brain, and this is music. Yeah. So these are different time scales in unimodal regions, sensory cortex, higher order transmodal, like the default mode network. And as I said, the transmodal, the DMN has longer time scales, unimodal shorter. Now so these are the different time scales. Now you present music to the robot. Now imagine in your robot, you have only the faster time scales. Here, the blue stuff. Yeah, but the robot lacks your slower time scales. Meaning, this is music presented in all time scales. And music is a paradigmatic example of a multi-temporal, different time scales involving input. Yeah, even more so than language. Yeah, and let's say your robot has only the faster time scales. Your robot will always dance too fast because it doesn't capture the longer time scales of the music. Now, your robot has only the longer time scales, but not the shorter ones. Meaning your robot will dance too slow because it doesn't capture the faster. So now you see it will only integrate everything, and which is always too slow. You need to integrate both. You need to have slower and longer and shorter time scales. And then you dance ideally to the rhythm of the music. So imagine, typical example, actually, as a psychiatrist, I know this very well. When you're severely depressed, your brain is too slow. And you can literally see this in the patient that they cannot follow fast rhythms. They always lag behind. So now imagine if you have the feeling you're always lagging behind, you always cannot follow my speech, and now I try to speak a little faster and you cannot follow, it becomes more and more difficult. Yeah, of course you become depressed. Yeah. Yeah. And then you withdraw, you become depressed, and you say, oh, maybe it's my thing. You have all this rumination. So it's a consequence of that. Yeah. So see, as I make it clear for time set, and of course, current AI only has a very limited time scales. They don't even explicitly model that in their models. Yeah, to the very short time scale for the task at hand. That's why artificial intelligence are not really adaptive. The advantage of the human, they have all these different time scales, and they're very adaptive, but they're not good. They're good in many things, but they're not extremely good, excel in one particular thing. The current AI excel in one particular thing, but are not adaptive. Yeah, so there's always a price to pay. So interesting thing, let's say, if you have sort of these different dimensions of consciousness, form, level, content, and this is from our paper where we basically classify the different states of consciousness, minimal conscious, schizophrenia, psychedelics, blah, 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 blah. Maybe for AI, if we really build different time scales into our artificial robot, maybe here, or maybe we need to extend this graph and put the AI here. Yeah. So this is the interesting thing where, of course, as a scientist, I'm very, very interested in, and I hope you can also use this for psychiatric stuff. On the other hand, you also need to consider the ethical applications because you don't know what this robot might do with its timescales. Yeah. With that, I come to the end. I think it's clear. I talked to you a little bit timescales, energy, power, waves, and you probably know this, that I said that's what we really need, what I call spatiotemporal neuroscience. The problem with current neuroscience is only looks for these functions and look at the neural correlates, and then at somehow here there's another arrow you could basically for consciousness, but I think it's a deeper layer of the brain. It's the global brain, it's the dynamic, it's the time scales, and that's what I call spatiotemporal neuroscience in this paper. So maybe we really need to consider the brain dynamics and how it translates into mental dynamics. Yeah, your thoughts, your emotions are not static; they're continuously changing. Yeah, and we investigate now these dynamics of your thought. It's pretty crazy stuff, mental dynamics. Yeah, but it's exactly like the seaside. It's continuously changing, the wave pattern continues changing depending upon the environmental context, if there's a lot of wind or not. Same in the case of the brain waves continuously change. There's a certain pattern in there depending upon the context of the body and the environment. And with that, I close. That's why I bring out next year comes a book for broader audiences, a book of neurowaves. And with that, I leave you. Thank you very much.
Thank you, Professor. It was a really great presentation. We need time to integrate all that. Questions on Q&A function, please. So this book, Neurowaves, it will come out in 2023.
Correct, next year. Yeah, okay. And it's written for the broader audience and discuss the waves, different disorders, different self-consciousness, and it's yeah.
We will look into it and hopefully you can sign it.
I'm happy to do that. Yeah, but then we meet in person. We need to meet in person.
Yeah, we will try to show you the castle.
Okay. Yes. I would love to see that. Indeed. Yeah.
We have a question from Martin Peters. Do the time scale of consciousness function similarly in a way to clock speeds of processors in computers in order to regulate all processes?
Yeah, I think so. Usually clocks have only one time scale. Yeah, I mean they have one time scale. You have to imagine that you have multiple clocks there, and they're all on different speeds. So it's not just the time change, the 6 hours delay. So imagine the clock. So what 1 hour in one clock is 10 minutes in another clock. That's the way you have to imagine different time scales. And now you imagine you have sort of 100 clocks sitting there. Yeah, you have 100 clocks sitting on your wall, and each clock has its own speed. Yeah, so for one clock, an hour is 10 minutes, another clock for 1 hour is 5 minutes, and so forth. Yeah, and now imagine all these clocks are somewhat coordinated. It's amazing. Yeah, I mean, the more I get into this basic stuff of the brain, I'm really wondering why we're usually functioning relatively well. Yeah, until we have to go to a psychiatrist. Yeah, but it's really amazing. And how are these different clocks with the different time speeds synchronized? Probably by relation to continuous input from the body and the environment. Yeah, because that gives you some kind of synchronization relationship among these different clocks, whose time scale are all sort of independent of each other. Yeah, but apparently let's say the breathing provides a very strong rhythm to synchronize these different clocks. Yeah, you can see that in the brain. Yeah, or as I said, example of music. Yeah, suddenly all these 100 clocks, I'm always pointing here towards the wall here. When you have 100 clocks there, and each one clock is 10 minutes, 1 hour, the another 5 minutes, 1 hour, and so on. Suddenly now these clocks are somewhat synchronized with the music. Why? Through the corresponding time scales in the music. Yeah, maybe in music there's one certain rhythm where you have where 1 hour corresponds to 10 minutes, let's say, another layer, let's say the cello in the background, they're a little slower, where 2 hours correspond to 5 minutes, so they can synchronize with all the clocks in the brain. Yeah, that's why we're always continuously aligned with the environment. This is often neglected. Yeah, and that's what is consciousness about. You experience yourself as part of the wider environment. Yeah, even here with the Zoom. Yeah, I'm not experiencing just myself. I experience myself as part of the Zoom screen. Then I relate myself to you because I see you guys on the Zoom screen. Then I experience myself here as part of the wider laptop screen, and I can go on for hours. Yeah, skip.
Good. Another question is, it is possible to explain in more detail what are the timescales, but I think you already did it in some way.
Yeah, just imagine the clocks, what I just said, or the different window sizes. Yeah.
If depression, another question from the same yes. If in depression we have a low time scale, can we use faster waves, gamma waves, to improve the situation? Thank you.
Yeah, that's exactly what indeed we do this. So we observe that, for instance, in visual cortex, activity is really too slow. You can see this in the brain, and you can also see this in psychophysical visual perception task. They perceive visual input as more static and not as dynamic. Yeah, so they can not follow the dynamics of the stimulus. Yeah, and indeed we have one study where we then try to give some magnetic stimulation, transcranial magnetic stimulation of the visual cortex. Yeah, and basically to fasten their perception, to fasten their brain activity, and then fasten their perception. And of course, if you have shorter time scales, your perception becomes more dynamic. Yeah, for instance, my movements, you can follow the dynamics of my movements because I assume that your visual cortex has the time scales. Now, if you don't have that time scale, the depression might perceive the same movements like this. Yeah, because you lack the faster time scale. Now imagine how you feel when you perceive this, as everything is too slow. Of course you become depressed.
Okay. They are not letting you leave this conference too soon. Another question. Would the external stimuli synchronize the clocks, or might there perhaps be a hidden master clock that functions as a musical conductor in response to the external stimuli? Might the thalamus perhaps be responsible for this?
Well, that's a lot of questions in one. It's nestedness, yeah. Nestedness of questions here. No, a good question. So first, the second question, is there a conductor? No, there is no conductor in the case of the brain. I mean, this is often been discussed as sort of what is called homunculus. There is no master clock. That's the fascinating thing about the brain. There is no master clock, that's for sure. However, then you say, what is it possible to make them somehow interacting with each other? This is a commonly shared exposure to continuous bodily input or environmental. Yeah, so you have the 100 clocks on the wall. They're all different speeds, all different time and everything. But when they're sort of exposed to a common environmental input like music, they're somewhat synchronized with each other. So if you want to say so, the environment of the body take on the role of the conductor, but it's not the same. It's not just one time scale. Yeah. Definitely subcortical in structures like thalamus, and if you go further down, midbrain, rougher nucleus, are definitely relevant because they modulate the time scale of the cortex. And indeed, that is not clear. So we try to investigate these subcortical timescales, which is very difficult in imaging because you don't have the signal resolution and the temporal resolution down there. So it's a difficult one. But for sure, you have this neuromodulatory input, serotonergic, rougher nucleus in depression, and they often obviously act through the thalamus and then on the cortex. Again, I would probably take a whole brain view here. You have to consider that in conjuncture. And it's absolutely right. It's a very corticocentric view here, but it is more due to the it's not a claim, it's more sort of due to the methodological limitations we have. So definitely, and the subcortical regions at their own time scales, obviously. They're usually shorter. Yeah, that's for sure.
Good. We are more than happy to welcome you again, because I think we need more talks with you. So thank you for coming. And probably next year we will have it in person. So if we do, then we are going to show you the castle. That's for sure. Thank you guys for being here. We will take a break right now, the lunch break. So tune in, because after we will have Stephen Govea, which is a very, very nice person, and you will hear him talk about AI and ethics. But we will have also Markiewicz Mihalko, which also has a glimpse of the future, if you want. He invented, I mean, he's a part of the group who already launched an application that is giving therapy based on an AI engine, an artificial intelligence engine. So this will be interesting. And we will have also the panel, a panel of discussion between Stephen Govea and Mihalko Markiewicz, talking about the future developments, implication, ethics, limitation of artificial intelligence and problems related to it. So we will wait you after the break. We will start at 14 hours and 40 minutes. So let's have 40 minutes of good food. Thank you, Professor, again. Bye.
Okay, bye. Have a good day. Thanks.
Thank you.